What about primes, twin primes, and the Eratosthenes sieve? Let us call 1, the prime numbers, and 2, the twin prime numbers. It may sound weird, but we are already halfway of our goal here. Let us add the minus sign before these two digits and we are done. Of course, this deserves a little bit more explanation, and therefore, we will provide it in the main part of this video. The sieve of Eratosthenes is an ancient algorithm for finding all prime numbers up to any given limit. It does so by iteratively marking as composite the multiples of each prime, starting with the first prime number, number 2. The multiples of a given prime are generated as a sequence of numbers, starting from that prime, with constant spacing between them, that is equal to that prime. The remaining unmarked numbers are the searched primes. The earliest known reference to the sieve is in Nicomachus of Gerase's Introduction to Arithmetic, an early 2nd century AD book, which describes it and attributes it to Eratosthenes of Cyrene, a 3rd century BC Greek mathematician. It is one of the most efficient ways to find all of the smaller primes and may be used to find primes in arithmetic progressions. The purpose here is to exploit this sieve in order to prove the infinity of primes and twin primes. Starting the routine with 2, removing strict multiples, then taking smallest remaining integer, again removing strict multiples, we will call the last prime on which the algorithm is exercised the current prime. We are interested in the primes, and, later on, in the twin primes, which means we are interested in the list of integers which are before, or left of, the current prime. But all we will do is to study the integers after the current prime, and later on, the current twin prime. Our main, or rather our almost sole interest, is to show that what happens after the current prime, is in a very close manner, what happens before it. One is an image of the other side and vice versa. All the information found on one side, is also the information gathered in the other. There is all, for our purpose, on either side, and not more is really useful. We will call, by the terminology pseudo, the elements remaining at each step on the right side of the current prime, that is, after the current prime. So what we have to do now is 1. To explicit the link between the two sides of the current prime. 2. To find some exact mathematical relationship governing the right side of the current prime. 3. To use the result to conclude on the left side of the current prime. Notions related to the distance between objects in this study can lead to pernicious confusion. For the sake of clarity, let us introduce precise terminology. We will have to define either isolated integers, or pairs of integers. We will call gap, the distance within a pair of numbers, and we will call spacing, the distance between the studied features, which are either isolated numbers, or pairs of numbers. Thus, for the pair of twin prime numbers, 11 and 13 for example, considered as one object, the gap is 2, while for the two pairs of integers, 11-13, and 15-17, considered as two objects, the spacing is 4, and the gap is 2. So let us start now. We are going to apply the Eratosthenes sieve beginning with 2. We call entry the list of integers up to the current prime, and we call cycle 1, cycle 2, cycle 3, and so on, all the repeating pattern of integers with equal spacings that we observe after the current prime. As for so far, we get one element per cycle, which are 3, then 5, then 7, and so on, all separated by a spacing of 2. Proceeding to the retrieval of the multiples of 3, we get 2 elements, the whole set separated by a 2 by 3 spacing, that is a spacing of 6, with repeating pattern to infinity. Likewise, retrieving now the multiples of 5, we get 8 elements, the set separated by a 2 by 3 by 5 spacing, that is a spacing of 30, with again repeating pattern up to infinity. The Chinese theorem explains the increase of the spacing by a multiplicative factor pi, where pi is the current prime. As for the total number of integers remaining in each cycle, it is not difficult to prove that it increases, at each step of the routine, by a multiplicative factor, pi minus 1. So we get 2 minus 1 equal 1, then 3 minus 1 by 1 equals 2, then 5 minus 1 by 2 equals 8, and so on. So whatever irregularities in the patterns on the left side of the current prime, spacings and numbers of integers on the right side are precisely linked, which was our number 1 goal, dealing with isolated integers. Let us do now the same thing with pairs of integers, separated by a gap of 2, that is, with pseudo-twin primes. The Eratosthenes algorithm is executed exactly like before. But we are now adding an extra line to our initial tables. This line contains the 2 gap value as a reminder, so that we can easily keep track. The current prime is again the prime on which we apply the multiples retrieval, but this time, the cycles are identified 1 prime ahead of the current one, that is the index is not I, but I plus 1. The spacing between cycles increases exactly like before, that is, by a multiplicative factor pi, when the current prime is pi. The number of elements in each cycle is also increasing like before by a pi minus 1 multiplicative factor. But this time, what we are interested in is the number of pairs, with gap 2 in each cycle. It is not difficult to prove that the multiplicative factor is pi minus 2, once the initial list, exception to the rule, has been given. So starting with the current prime 3, as step 1, the multiplicative factor is thus 3 minus 2 equal 1, then 5 minus 2 by 1 equals 3, then 7 minus 2 by 3 equals 15, and so on. The summary, so far, is that the proportion of the remaining elements in a cycle, in the first instance that we examined, was pi minus 1, divided by pi. In the second instance, the proportion is pi minus 2, divided by pi. Using Merton's third theorem, we can prove a general expression of which the third relation on the screen is a peculiar example. According to the prime number theorem, the cardinal p of x, of prime numbers, less or equal to x, is equivalent, when the real number x tends towards infinity, to the quotient of x, divided by the Neperian logarithm of x. A succession of links can then be provided, up to the asymptotic number of twin primes. The same types of links can be done with any spacing between pairs of pseudo-primes, and Hardy-Littlewood formula can be recovered in this way. Of course, we do not say here that these arguments are sufficient, and therefore rigorous, to be a proof of the infinity of twin prime numbers. We gave here only a general summary of the tools necessary to get to such conclusion. At the end of the video, the viewer is given an online link to a comprehensive proof. In the said proof, we provide a mean-around and a majorant of the numbers of twin primes at a given x abscissa. These two items have same asymptotic expression and makes up the first part of our study. The second part of the study is focus on another strategy, which is not to evaluate the numbers of items at given abscissa, but the distances between these items. Indeed, if a finite distance exists between two objects, it means there is a successor to the current one, and so on, that is, there are an infinity of them. We choose again the right side of the current prime, or of pseudo-twin prime, according to what object we intend to study. When executing the Eratosthenes algorithm, we know that we have increasingly more integers remaining, in relative proportion to the effectively prime numbers, or twin prime numbers. So that may seem a potentially totally stupid approach. But, between the current pi prime, and the pi to the square boundary, only one kind of integers can still exist, primes. Indeed, let us insist and repeat, between the current pi prime, and the pi to the square boundary, only prime numbers subsist. If we find some general property on a whole cycle, that property will also apply between the pi prime value, and the pi to the square value. So let us introduce the adequate property. It is the maximum spacing between the studied objects, either pseudo-primes, or pseudo-pairs of primes. By Bertrand's postulate, and Chebyshev's proof, the maximum spacing between a prime and his successor, is twice its value. What about then between a pseudo-twin prime and its successor, in a Eratosthenes cycle? The answer is, twice the sum of all primes, up to the current one. The viewer can examine the results for the two types of objects studied here. Here are the results for the pseudo-prime numbers. Here are the results for the pseudo-twin prime numbers. It is quite easy to get an explanation for the maximum spacings between the pseudo-twin prime numbers in an asymptotical perspective. For more on this, the viewer will refer to our online links at the end of the video. Let us note, however, that exceptions to the rule are not forbidden and may occur relatively often. Indeed, as we can see, starting at pi equal to 23, until pi equal to 53, the maximum expected spacing in a cycle may be higher than expected. This is due to an overlap of some combinations of spacings with another combination, thus creating the said exceptions. But, when that instance effectively happens, favorable case of further enlargement, at this specific place, is very small, and the maximum value won't progress. Not changing, this maximum spacing will progressively, as the sieve step increases, return within the standard expected value for this step. In order to confirm this asymptotic behavior, another way is to look further into the actual values displayed previously in the table. For the two categories of objects, pseudo-primes, and pseudo-pairs of primes, there will be again the same kind of relationships. Let us go back and focus on the second kind of mathematical objects. The first line of spacings increase in a very simple way, which is by the multiplicative factor pk-2, where k is the index, not of the current step, but of the former one, that is, index k equals I-1. So we have here a recurrent formula, which give us a result up to infinity. We need only the first value of this first line series to get all of the values in the line. Let us rewrite the data of the spacings between objects, but this time changing lines to columns. We have represented into parentheses the spacings needed to get all of the next ones. Indeed, the Eratosthenes algorithm gives way to systematic relationships between successive components. Nevertheless, the number of initial values required, increases with the line index j. The increase of the initial data requirement is approximately half of index j. Back again to our initial table with now, quite a good approach to the line evolution, the column evolution remains still with a lot of questioning. Here the viewer is given a graphic of the number of instances, as the line index increases. One can see the exponential drop of the populations, in regard of spacings, with the convexity of the curve turned towards the bottom, confirming in the same time the existence of maximum value of spacings. There is a lot more still to say. Plenty more. The place to grab all the information is at either of the following links. We wish you a pleasant reading. What about some comments underneath after that?